meaning the difference between inter and intramolecular forces of attraction. Intra, they are responsible for chemical changes. This intra. Inter is responsible for physical changes. In the physical changes, melting point, boiling point, the change in state. Remember, physical change means change in state of matter. Change in state of matter means solid to liquid to gas. So whenever you see a change in state of matter, then you can call it as a physical change, which is governed by these physical properties: melting point, boiling point, delta H of vaporization, fusion, sublimation, and vapor pressure. Please include this. Vapor pressure. If IMF is more, intermolecular forces of attractions are more, then the boiling point is more, the melting point is more, the delta H of vaporization is more, fusion is more, sublimation is more. What happens to vapor pressure? This is the only thing which will be less. Rest all will be more. So these are the things which we need to understand, because questions will be based on that. So let's start now IMF. So very first, the weakest attractive forces. When I say IMF, then it means I'm talking about covalent molecules. Covalent. When I say interparticle attraction, like ion to ion attraction, ion attraction, it is present in ionic compounds. Ionic, right? Now let's see. I think I explained you the meaning of temporary dipole, induced dipole. We are clear about it? Last time, electrons are moving for an instant of time. Electrons, they go on a particular side of the atom, creating a partial negative there. The other side will become partial positive. This partial positive will attract the electron of the other molecule. Now it is partial negative. This is partial positive. So you can see that how the induced dipole, how the dipole is induced. The dipole is induced. Is it okay? Okay, so this is induced dipole, and it depends on the electron cloud, because it's distortion of electron cloud. This is called as distortion. This is uniform distribution. These are, but this is distortion. Distortion of or polarization. Remember this word, polarization of electron cloud. Now this polarization of electron cloud depends on two factors. Polarization or polarizability. Polarizability of electron cloud to get this induced dipole. This is polarizability. You can see this is totally non-polar. But all of a sudden, electrons have moved to one direction. So there is a partial negative, partial positive, which is creating partial negative, partial positive on the others. So this polarizability is distortion of electron cloud. It depends on two factors. First, it is amount or the size of the electron cloud. More big size, more easily polarizable. Second, it depends on the surface area of the molecule. How to compare the size of electron cloud? So they have taken the molar mass here. Molar mass. Just compare the molar mass. More higher molar mass means more number of protons, more number of electrons. Like if I give you CCl4 and CH4, definitely here the amount of the electrons are very high molar mass. So you just compare the molar mass of these two. So which one is more easily polarizable? Which one is more easily polarizable, CCl4 or CH4? CCl4. You know what is the state of CCl4? It's liquid. And what is the state of CH4, methane? It's a gas. So this can be a question. CCl4 and CH4, they will say it's liquid and gas. Explain why. Is this molecule polar? This one, CCl4? Draw the Lewis dot structure. No, it's non-polar, right? If it is non-polar, sorry, if it is non-polar, this one is also non-polar. Then both of them are with LDF, London dispersion forces, induced dipole, temporary dipoles, which depends on the how big is the electron cloud around in that molecule. Okay, so which one has stronger LDF? Which one has stronger LDF? CCl4. Because of the big electron cloud, which is easily polarizable. Include this knowledge in your language. CCl4 is more polarizable than CH4. So CCl4 has stronger IMF, stronger London dispersion forces than CH4. So CCl4 is liquid, CH4 is gas. So this is a question, important question. And remember these 2 points. You can write it down somewhere. Polarizability. Now this polarizability can be introduced when there is a non-polar molecule next to a non-polar molecule. Like these two are non-polar. And that dipole is induced. But the same polarizability can be introduced with the help of ions. You take a cation and put a non-polar molecule, this kind of molecule, next to this cation. So this will become distorted. This is electron cloud. The red is electron cloud. So you can see how it is distorted. And there is a temporary dipole. So what kind of this attraction called as? What is the name of this attraction? Ion induced dipole, right? Like for example, if I give you Na plus in some non-polar solvent CCl4. So what kind of attraction between these two? Name the attraction. They will say name the attraction. So what kind of attraction? Ion induced dipole. So you try to identify what is here. This is ion. And what can be here? Induced dipole. Name it like this. If I give you Na plus attracted to water, oxygen of the water, what kind of attraction is this? Name it. You know that water has that hydrogen bonding, dipole, and LDF. All three are there in water. What is this? What is this? Amodita, can you change your name, please? What is this? Ion. And what is here? Dipole. It's called as ion dipole. You know, in the unit 4, I'll discuss hydration. Hydration. So this is a question. Hydration has ion dipole attraction. Ion dipole. Try to name no hydrogen bonding. Don't say ion hydrogen bonding. This Na plus is not making hydrogen bonding. You can say this Na plus is attracted to the delta minus of the oxygen, which is a dipole. So it's ion dipole in hydration. Hydration means that NaCl solid is going into water. You're adding water, dissolution. Is becoming Na plus aqueous, Cl minus aqueous. Hydration is very important word. So this Na plus is getting surrounded by water, not by one water, by 6 water molecules, 6, like this. Aqueous means surrounded by water, hydration, hydrated. It's not a crystallization, water crystallization, the one we did hydrated salts. No, it's in the solution how these ions are surrounded by water molecules when they are totally soluble. This is a NaCl is a soluble salt in water. This is called as hydration. Na plus getting surrounded by water. This hydration, this process where each Na plus is surrounded by 6 water molecule like this, is it endo or exo? This one. It is exothermic. So you remember we were doing delta H lattice. I told you the word delta H, right? H means heat, enthalpy. Yes, change in heat. So this is delta H hydration. Delta H hydration, which is, according to our understanding, is always exothermic because attractions are made between ion, this ion, and dipole, strong dipole. Water has very strong dipole. So it's a very strong ion dipole attraction. So please write down this. I'm not going to repeat this because it will come again. If I give you Mg2 plus, surrounded by water molecules, can you tell me in which case the delta H of hydration is more? In which case and why? Yes, in water, in Mg2 plus it is more. Why? What's the reason? Mink, you're right. Give the reason. Yes. Because all these forces of attraction, whatever we are talking about, maybe weak, maybe yes, all the forces of attraction, you're going to call them as Coulombic forces of attraction. You're going to use this equation F equals to K times Q1, Q2 over R squared. And this is the major factor. If this is more, F is more. This becomes later on secondary factor, but this is also major. When their charges are same, then compare size. When charges are same, you can compare size. Like I can compare in NaCl and in NaI. Because here charges are same. So what I'm going to compare? I'm going to compare the sizes of Cl minus and I minus. Yes, very good. Akash, good. Okay, so I think we are understanding things, right? So now the next is you can induce a dipole in this non-polar molecule. This is non-polar, completely non-polar. You can see how the electron cloud is symmetrically distributed. Now you put a dipole next to it, means water. Let's say take water. Water has a dipole like this. You put water and CCl4. Water and CCl4. Do you think what is CCl4? Non-polar. So what kind of attraction they can develop? Dipole, induced dipole. Okay, I'm giving you one more important line here about the solubility. So please write down. We start practicing this also. Solubility. Like dissolves like. Like dissolves like. It will come again in unit 3. What does it mean? It means that if IMFs are same, yes, if IMFs are same, like dipole, dipole, if both the compounds have the same IMF, they are soluble into each other. Because in that case, energy wise, things are compatible. Like, for example, if I give you water, water has hydrogen bonding. If I give you ammonia, ammonia has hydrogen bonding. So you can break the hydrogen bonding of water, you can break the hydrogen bonding of ammonia, and they can make new hydrogen bondings. So the energy needed to break and energy released when new are formed, they are compatible. They are nearly same. So someone is giving money, someone is taking money. You know, money is a big problem nowadays. People can fight on it. Why? Because, oh, I've given you so much, you are returning so less. Same is nature. The money here is energy. Energy needed to separate water molecules, to separate water molecules. Energy needed to separate ammonia molecules, ammonia. This energy needed, if it is very large, then they are not interested in each other. But when energy needed and energy released, when ammonia and water coming closer, if they are of nearly same, then they are soluble into each other. And here they are same because they are nearly same IMFs, hydrogen bonding. But do you think water is soluble in CCl4? Do you think? No. Because energy released in this ion induced dipole, in this dipole and induced dipole, this one, the energy released during this interaction between this and this is very less. This is weak attraction, weak. And the attraction among the water molecule is strong. So energy needed to break attraction is large. Energy released is less. So not permitted. So nature will not permit this solution. Water is not soluble in CCl4. So we'll start discussing this also, right? Like dissolves like. Okay. So I was telling you to practice this word. Polarizability is how easily that electron cloud can be polarized or can be distorted to create a dipole. Distorted, right? Now this is unpolarized non-polar molecule, but this is now polarized. There is induced dipole. So please start practicing this word, start using it in your explanation also. And this polarizability depends on the number of electrons, how big is the electron cloud, and if you can easily diffuse it. Diffuse means distort it. And it also depends on surface area that is not mentioned here. So please include it. surface area. You can see it in my notes, right? Those who are looking up for more and more practice question, I do have one more book. That is also Zumda, but that book has only questions. So I'll upload the book there on the website only. The full book. I'll upload the full book and you start doing questions from there. I'm very happy that you people are doing really good, all of you. And you are practicing quizzes. I can see submissions from Akash was doing, Amodita was doing, Mayank is already into it. So I'll give you one more book. You can download from here also. If it can be uploaded. Doing more questions, those who are targeting chemistry Olympiad, this one. Please download this book. And I will upload it on the website also. In this book, like right now we are doing chapter 8 of the book. I think the name is Solids and Liquids. We are discussing IMF. We are trying to understand why it is solid, why it is liquid, why it is a gas. So the chapter name is Solids and Liquids. Okay, answer this question, children. And remember, this book is saying AP Chemistry, but all the topics are not from AP Chemistry. AP Chemistry you're learning here. So there are many, many chapters, many, many topics, which is not the part of AP Chemistry. Okay, so take care of that. So can you explain why the melting point is increasing? Yes, please. So first of all, look at the molecules. Look at the molecules. So what are they? Polar, non-polar? Okay, can you tell me, Amodita, why? The Amodita is saying they all are non-polar because carbon can make only 4 bonds in a tetrahedral. They all are tetrahedrals. Symmetrical. All atoms are same. Symmetrical. All dipoles cancelled out. Amudita, you are understanding this? They are symmetrical. So what kind of IMF they have? LDFs. And LDFs depends on molar mass and size. So what is happening to the molar mass as you are going down? Yes. What is happening to the molar mass? Increasing. What is happening to the size? Size is also increasing. Surface area. Surface area is also increasing. London dispersion forces, LDFs, they are also called as dispersion forces. I think this word is more popular with the teachers in the USA. So if your teacher is using dispersion forces, you can use that also. LDFs, dispersion forces. AP is more into this word, dispersion. So H2 is gas. You can explain why, right? If I compare H2 gas with Cl2 gas, which is going to have stronger IMF? Which one is going to have stronger IMFs? Cl2, right, Akash? And why? Give 2 reasons. Bigger size and bigger molar mass. Yes. So electron cloud in Cl2 is more easily polarizable. Okay, can you explain this trend here? What is happening to the melting point and boiling point as you are going from helium to radon? What is happening? They all are gases. Okay, give the reason. What kind of IMF are there? And LDF depends on molar mass and surface area. And what is happening to molar mass and surface area? Is increasing, yes. Okay, good. These are very simple questions now. Okay, can you explain this that F2 is a gas, Cl2 is a gas, Br2 is liquid, I2 is solid. Explain why. Explain why. Yes, yes. They all, you have to start like this. All these molecules are non-polar. The only attractive forces is London dispersion forces. And LDF depends on molar mass and surface area. Molar mass and surface area is increasing as we go from F2 to I2. So that is the reason I2 has the strongest, F2 has the weakest, I2 is in the solid, and F2 is in the gaseous form. Break the bonds. Amodita, don't use this word. You're not breaking the bonds. Are you breaking I2 to I? Are you breaking inter or intra? When you're melting them or boiling them, are you breaking intra or inter? Yes, so don't use bonds in your explanation. Okay, what you can say, we are to break the attractive forces, or you can write IMFs, right? To break the attractive forces. So this AP is taking it very seriously. Break the bonds, that word, they are taking it very seriously. We are not breaking bonds, we are breaking only attractive forces. It's a physical change. Okay, so ready for this question? Can you explain? I give you the formula here. This is CH4. This is C2H6. This is C3H8. This is C4H10. These are organic molecules, hydrocarbons, hydrocarbon, right? Hydrocarbons are made up of only hydrogen and carbon. We did this in empirical and molecular formulas. Combustion of a hydrocarbon gives you CO2 and H2O. So these are hydrocarbons. Can you see the melting point here? It's increasing, right? Explain why. So first of all, these molecules are polar or non-polar? I told you to memorize one line. All hydrocarbons are non-polar. Yes, because the difference in electronegativity of carbon and hydrogen is very, very less, 0.4 or even less than that. So bond is not polar. The chemical bond itself is non-polar. Okay, good. So what type of attractive forces? LDFs. So what is happening to LDFs as you go from methane to butane? Increasing. Give two reasons. Two reasons. So in which case the electron cloud is more polarizable. Which molecule is more polarizable? Yes, like this. Start using this word polarizable. The butane has more polarizability than methane. Now I'm giving you another example. Oh, C5H12. This is the molecular formula. Now this can have all the 5 carbons connected to each other in a straight chain like this. You know that carbon can make maximum how many bonds? 4. So one bond is made. So how many hydrogens on this carbon? 3. How many on this? 2. How many on this? This is called as normal pentane. Don't worry about the names. Normal pentane. Straight chain. We say no branching. It's a straight chain. C, C, C connected in a straight chain like this. Normal pentane. The molar mass is 72 grams per mole. This one also has the same. But it can have a branch like this. 4 carbon in the straight chain and 1 carbon here. Now it's a branching. This is called as a branch of a hydrocarbon. These are hydrocarbons. Put hydrogens. How many hydrogens on this carbon? How many hydrogens on this carbon? How many hydrogens on this carbon? On this carbon? On this carbon? Okay. This is called as isopentane. Isopentane. Here one methyl has come in the branch. Oh yeah. Yes, you're right. Who is this? Akash, thank you very much. Because it's already bonded with 3 carbons, so only 1 more hydrogen. Perfect, Akash. Good thing. Okay, this is isopentane. Now I'm going to make another. These are called as isomers. Iso means they have the same molecular formula, this, but they have different structures. So there is a branch here. Branching has taken place. Now you can have 3 carbons in the straight chain and 1 carbon here and 1 carbon here. Can you put hydrogens on this? This, how many on these carbons? We call them as terminal carbons. Terminal carbons are always with 3 hydrogens. You see, this is terminal, 3 hydrogen. This is terminal, right? And it is called as neopentane. Is there any hydrogen on this carbon, children? No. Okay, this is neopentane. These are the 3 isomers of the pentane with the same molar mass. Now, let's see the surface area. Which one has the highest surface area? Just check the surface area. Which one has the highest surface area? Oh no. Okay, children, to understand this surface area, normal pentane. So I'm giving you one example, Akash, to understand the surface area. If I give you a bed sheet and you spread it uniformly, totally spread out, and you make a bundle of it. Bundle means just put a bundle, wrap it like this, like a bundle, and throw it on one corner. So in which case, the surface area of the bed sheet is more when it is uniformly spread out on the bed, or when you have made a ball of it and thrown it in one corner. Like when you want to put it in the almirah, you make a ball of it and put it in the almirah. So in which case, uniformly spread it one. This is totally spread out. This is spherical. So spheres have minimum surface area in mathematics also. Water droplets are in the form of sphere. When they are falling down, they acquire the shape of a sphere because spheres have minimum surface area. That's why they acquire that shape. They are not flat, they are not spread out. They are like a sphere because of the minimum surface area. Remember this line. So can I compare their boiling points? Because molar mass is same, so don't compare molar masses, compare their branching. More branching, more it becomes spherical. More spherical, less surface area. So who has the highest boiling point here? Highest and the lowest. And the lowest is, and it's true. You can see here. This is neopentane. See, like a sphere. Normal pentane. Can you see the structure here? This is a very important question for chemistry Olympiad or AP chemistry. Very important. Can I ask one more question based on it? Ready? I'm going to erase this. So remember this line, Amodita, Mayank, and Akash. I'm going to use this again. Water falls, free falling water, like raindrops. They're always spherical. Why? Because in the spherical form, it has minimum surface area, minimum surface tension. So we'll discuss that. Okay, another example is butane, C4, this one, H10. Smaller masses, 58 grams per mole. You can have all the 4 carbons in the straight chain like this. Then you can put hydrogens, 3 here, 2 here, 2 here, and 3 here. Then you can have one branching, means 3 carbons in the main chain and one branching. You can put hydrogens here, here, here. So what is happening with the branching? It's becoming like a sphere, more spherical. It decreases surface area. So who has higher boiling point? This is normal. Normal means straight chain. And this is iso. I'm going to start a YouTube channel. I will be teaching organic chemistry there. Anyone interested, do let me know. I'll give you the link. It's free and you can join me. It's free and maybe I will be doing live streaming or maybe I'm going to post the videos. Live streaming is better, but I'm not familiar with the live streaming concept of the YouTube channel. So first I'll try to make myself familiar and very soon I will be on live streaming for organic chemistry. I love teaching organic chemistry. Organic chemistry is really wonderful. Okay, so we are good with this? Normal butane and isobutane. Okay, one more question before we go to the next thing. There is a molecule CH3, CH3. This one, ethene. There is a molecule CH3, CH2, OH. If you remember, we did this molecule in empirical and molecular formula combustion analysis. Ethanol. We derived the formula. Out of this ethene and ethanol, according to your understanding, which one is going to have higher boiling point? Which one is going to have? Yes, give reason. Yes, you're right. All of you are right. Give reason. No, 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 no. Always first thing, compare IMF. This is completely non-polar, isn't it? The first thing is compare IMF. This is a second factor now. This is non-polar. It has only LDFs. Whereas this one is it non-polar? No, it's polar. It has hydrogen bonding. Hydrogen bonding also. OH, hydrogen on the oxygen. This molecule has hydrogen bonding. is polar. Then answer. Because first you have to compare the stronger one. In the smaller molecules, small molecules, we compare stronger IMF first. Their IMFs are not same, so I'm not going to compare their LDFs. I'll say ethanol has hydrogen bonding, dipole-dipole attraction, which is stronger than LDF. So ethanol has higher boiling point. This is liquid. This is gas. This one is liquid. Drinking alcohol. Ethanol is drinking alcohol. This is gas. Okay. Are they soluble into each other? Do you think ethane is soluble in ethanol? No. But if I give you this molecule, CH3OH, C2H5OH. If I say which one has higher boiling point? So first to answer this, then we'll see what we are comparing. Which one has higher boiling point according to your understanding? Yeah, okay. Now explain why. What do you think? IMFs are same. What is here? Hydrogen bonding, dipole dipole, LDFs. Hydrogen bonding and dipole dipole is exactly same in both the molecules, correct? Same here, same in both of them, exactly same. So where is the difference then? Yes, and the molar mass Mayank. LDF is different in both of them. In this case, only this molecule has that non-polar part. So molar mass is also less, surface area is also less. If I give you water, try to understand this. It's not a tough question. Out of these two, which one, according to your understanding, is more soluble in water? Which one? Yes, it is. Very good, Akash. Because here, this non-polar part is small. This is small. You know, if I give you C3H7OH, not C3, let's take C5. C3 is also soluble slightly. C5H11OH. If I give you this is not soluble in water. Now you can say, oh, what happened to your like dissolves like rule here? Not soluble in water. This one. What happened to my like dissolves like rule? Here, this London LDF non-polar part is big, very big. This is dominating. So in big molecules, the non-polar part, if it is more big, then it starts dominating. You can see here there's only CH3, here it is C5H11. So as this non-polar part, we call it as hydrophobic. Means, what's the meaning of hydrophobic? Water fearing. Means not soluble in water. Yes, repelling water. Yes. Not soluble in water. So that part, if that part is big, then it becomes not soluble in water. And this OH is hydrophilic. What's the meaning of hydrophilic? Water loving. Philic means loving. Phobic means fearing. We are using these words in chemistry, hydrophobic, hydrophilic. And why this is hydrophilic? Because IMFs are same, hydrogen bonding. Okay, so understand these terms. Okay, dipole-dipole forces. So which molecules have dipole-dipole forces? The one which are polar, the one in which the molecule is not symmetrical. The dipoles are not cancelled out, you know that. So let's draw the Lewis dot structure of SO2, sulfur, okay Akash, oxygen, oxygen, total valence electrons, 18, complete the octet of the oxygen with 2 lone pairs and a double bond. You know, this is how it's very happy. 0 formal charge. Put a lone pair on the sulfur, right? So how many groups around sulfur? Start answering all those standard questions. So what is the hybridization? What is the electron domain geometry? That we call it as electronic geometry. What is electronic geometry? What is molecular geometry? Is it symmetrical, not symmetrical? So is it polar or non-polar? So what kind of IMF this molecule has? Okay, they may ask you to draw the dipoles, which is very easy. Which one is more electronegative, oxygen or sulfur? So you can draw a dipole like this. This is delta minus, this is delta plus. You can draw a dipole like this. This is delta minus and this is delta plus. And there is a dipole due to lone pairs. Like this, lone pairs. They also exert a dipole. So the molecule dipoles are net dipole moment is not equal to 0 because it's not symmetrical, right? So there is a net dipole moment. The net dipole moment I can draw in the direction of the lone pairs, whatever is there. So there is a delta minus, this is delta minus, sorry, this is delta plus, tip of the arrow, minus, tail is plus. So there is a dipole in this molecule. So one SO2 molecule has a dipole which is attracted to another SO2 molecule like this. So these are dipole-dipole attractive forces. So this is your HCl. This is delta plus, delta minus. So if it is in the solid form, it's a molecular solid. So what are the attractive forces in this molecular solid? The major attractive forces are dipole, dipole. Can you see how properly it is oriented? Irregular repetitive arrangement, this minus next to plus, this minus next to plus. This is HCl, this is HCl, this is HCl. Such a systematic repetitive arrangement. This systematic and repetitive arrangement results in the formation of a lattice. In this lattice, all the solids, every solid except few, they all have lattice. So what's the name of this lattice? Molecular lattice, because these are molecules. What kind of attractive forces are there in this lattice? Dipole, dipole. Like we have one covalent network lattice. What was that? Diamond, graphite, strongest. Very high temperature to break them apart. Because there you have to break the bonds in the diamond and graphite because it's a network of bonds. Diamond is a network of chemical bonds. So Amudita, there we can see that we are breaking chemical bonds to melt diamond and graphite. It's like this. Network of covalent bonds. But here, when I'm going to melt it, I'm breaking this dipole-dipole, which are weaker. Akash, you're back. And these dipoles, you remember I used the word temporary dipoles. So temporary dipoles are, they are induced by the distortion of the electron cloud due to polarizability. So, but these dipoles, which are due to the polarity of the chemical bond, unsymmetrical molecules, they are permanent dipoles. Akash, you are here. You're back. So please ensure that you take your water bottle, everything before the class. Because if you miss lines, then watching the complete video again, it's a lengthy process. Okay, let's see why this molecule is polar in nature. Delta minus, delta plus. And there is a polarity, like there is a dipole like this. Is this part polar? This one? This part? Is this polar? It's a hydrocarbon type, right? So this, there is hardly any polarity here. So this is called as permanent dipole. And the molecule will appear, these are called as that electron potential maps. Electron potential maps. Nowadays in the books, they show these kind of maps. And what is the map is showing you? That how the electron density is concentrated here. Here, the one with delta minus. Here, the electron density is uniformly spread out. So this has only temporary dipole, but this one has a permanent dipole. So do you think these two are soluble into each other? These two? Are they soluble into each other? No, they are not soluble into each other. Why? Why is it so, Amodita? You are right. What is the reason that they are not soluble into each other? Yes, because the IMFs are different. This has only LDFs. This one has dipole-dipole. Is more energy is needed to break dipole-dipole. But less energy is generated when this molecule comes closer to this one to have induced dipole-dipole attraction. Induced dipole-dipole attractions are very weak. So amount of energy released is also less. So that energy is not sufficient enough to break dipole-dipole of these molecules. We are good? Okay, now the hydrogen bonding. Which three elements can show hydrogen bonding? I've already discussed with you. NOF. Akash, you took so much time. So next time you missed many things. Permanent dipole. And I introduced the word lattice, and this is molecular lattice. Then I explained again the covalent network, solid, diamond, and graphite. Okay, so hydrogen bonding is with NOF. So what is the condition? The condition is there should be hydrogen next to these elements. Nitrogen bonded to hydrogen. There is hydrogen bonding. Oxygen bonded to hydrogen. And fluorine bonded to hydrogen. Only then you can see hydrogen bonding. Right? Why is it so? Because the difference in electronegativity is high. Yes. So there is a big dipole. The difference in, see hydrogen 2.1. If you check hydrogen, if I put hydrogen here as 2.1, then in the immediate elements, hydrogen has the minimum. Chlorine, bromine, iodine, high, sulfur, selenium, tellurium is nearly same, but tellurium is more polarizable. So the polarity will be more. It's more polarizable. You know, down the group, polarizability. I'm using this word now. Down the group, polarizability increases. So hydrogen is very Not polarizable at all. Why? Hydrogen is not polarizable because it has only one electron cloud. It's very small. It has only one shell. It's not polarizable, right? So the difference in electronegativity here is very, very large. And due to this large difference in electronegativity, there is big dipole. Dipole is big. It's a kind of dipole-dipole. Hydrogen bonding is special dipole-dipole attraction because of the large difference in electronegativity, right? So if I give you CH3SH, CH3OH, can you tell me which one has stronger attractive forces? Yes, can you name the attractive forces in CH3OH? And in CH3SH? Yes, it has dipole-dipole and LDF. This sulfur bonded to hydrogen. If you see the Lewis dot structure of CH3SH, carbon is bonded to 4 groups. 3 are hydrogen and 1 is SH. This sulfur also has 2 lone pairs, just like oxygen here. Oxygen, when it is the central atom, it can have 2 single bonds. This is SH. Same with your CH3OH. 3 hydrogens. The molecule is not symmetrical, right? Here is oxygen with 2 lone pairs. Here, this part of the molecule can show you hydrogen bonding. This part of the molecule can show you only dipole-dipole. So this one has higher boiling point as compared to CH3SH. So these are very simple questions. You have to just see if you have any hydrogen next to any of these elements. Hydrogen bonding is a very special kind of attraction. The word is bond here, but again, it's not a chemical bond. It's not a bond. We are calling it as a bond because it's stronger. It is strongest as compared to dipole-dipole and LDF. So whenever hydrogen bonding is there and when we want to show, oh, in this molecule there is hydrogen bonding, we represent it by dots like this. If you make it like this, then it's a chemical bond, but it's not a chemical bond. It's a attraction. So that's why they make it like this. These are hydrogen bonds. These are not chemical bonds. You can see that. It's among the molecules. It's not intra, it's inter. What are intra here? This is intra. This is intra. It's a sharing of electrons, making a covalent bond. And the red one is inter. So when you are boiling, melting, you're converting your molecule into other state like solid to liquid or liquid to gas like this, then in that case you are breaking inter, not intra. Yes. We are clear about this hydrogen bonding? Children, can you give me 1 second? Yeah, by the time, look at this example. Okay, you can hear me? I'm back. Are we clear about these hydrogen bonds? This one, the delta minus of the oxygen of the water is attracted to the hydrogen of the other water molecule. And due to these hydrogen bonds, there is extensive hydrogen bonding in ice. Ice, low temperature. So when temperature is low, then the amount of IMF increases or decreases. Think about it. When the temperature is low, yes, increases. Ice has more extensive hydrogen bonding than liquid water. So if I compare ice with liquid water has less hydrogen bonding as compared to ice. This is a very important concept. I'm going to cover it. And due to this extensive hydrogen bonding, ice has different nature. Ice is less denser than liquid water at 4 degrees Celsius. Density of ice is less. Density increases when it melts. Yes, right. Okay, so all these things are based on these hydrogen bonding. Because when ice makes an extensive hydrogen bonding network, there are many gaps in between. Like here, like if this is, I show you the picture, okay? When this topic will come, I'll explain you with the help of pictures. So hydrogen bonding is clear to us. Now, due to this hydrogen bonding, we have very anomalous kind of graphical representation because you know that only 3 types of molecules can do hydrogen bonding: water, HF, ammonia. These are the one from the periodic table. Otherwise, there are many, but whenever there is a hydrogen on the oxygen, fluorine, and nitrogen, they make the hydrogen bonding. So if I take this nitrogen family and if I take this molecule NH3, then PH3, then your next molecule, next element there is A arsenic, ASH3, then antimony, SPH3. If I ask you to compare their boiling points, so all these are, remember what are these? All of them are polar. All of them are trigonal pyramidal, if you remember. The element is here, then it has 3 hydrogens like this. They all have one lone pair here. So if you draw the Lewis dot structure, they all are going to have exactly same Lewis dot structure because they have the same valence electrons, same type of bonding. Okay, so these are polar molecules. So they have what kind of attractive forces? Dipole, dipole. But one of them has very high attractive forces. Which one? Ammonia. If I ask you to draw the boiling point graph, here is the boiling point for this family, then don't you think that ammonia has higher? This is ammonia here, NH3. Then this one is pH3. But after pH3, what can I compare? After pH3, you compare LDFs because polarity is nearly same. They all are polar, so dipole, dipole. So you compare the LDFs. So what is happening to LDF as you are moving down, as you're going from P to arsenic to antimony? What is happening to LDF? Okay, because of the more polarizability, right? Because of the more molar mass. So after pH3, what will come? And after that, what will come? Can you see? And can you see that SPH3 is without hydrogen bonding? But because of its high molar mass, see here, This is SpH3. Its boiling point is very, very comparable to that of NH3. So in heavy molecules, remember this again, very important, like in polymers. In heavy molecules, LDF becomes dominating. If the molecule is very big in molar mass and in size, then LDFs, they try to dominate even these hydrogen bondings. Is it okay? So this is the graph of ammonia, which you can see here. Here. And now let's compare oxygen family. H2O, H2S, H2SC, H2TE. This is unique hydrogen bonding. But after that, there is an increase in size, molar mass, surface area. So just compare LDFs in rest of the molecule. You can see the graph here. See, water has exceptionally high 100 as the boiling point. And then, but now you can ask this question that why this water is exceptionally so high, because there are two hydrogens and the difference in electronegativity of oxygen and hydrogen and two lone pairs. Lone pairs also two. They also exert a dipole. So there is big difference in electronegativity. The molecule is very polar, is more polar as compared to ammonia. Ammonia has only one lone pair. The difference in electronegativity of nitrogen and hydrogen is less than oxygen hydrogen. Can you see the difference in ammonia and water? So answer my question. Which is easy to get converted into gas, ammonia or water? Which compound can be molecule? Yes, yes. You know, ammonia most of the time under normal condition is a gas. When you're going to do questions, you'll be seeing ammonia as a gas, like this. You'll be using this. Whereas water generally is in the liquid form. For the gaseous form, water has to come at this temperature, 100. And when we are working in the lab, do you think we are working at a temperature of 100 degrees Celsius? No. Lab temperature is 25. Right? So at 25, water is liquid. So are we clear about this graph also? Are you clear that why the boiling point is increasing in this area? Okay. Now let's see HF. The difference in electronegativity is very large, but there is only one hydrogen bond. So that's why it is lesser than water. You can see. And then HCl, HBr, HI. HF is higher than HCl. You can see. We're understanding this. So here again the same reason. Same reason that the London dispersion forces are increasing, the molar mass is increasing, the size is increasing. So it has stronger LDF. So boiling point is increasing. So that's the story about the IMFs. Yeah, here is water. Yeah, that's what I was trying to explain. The extensive hydrogen bonding in ice. This is ice. And you can see large gaps here. And you can see these hydrogen bondings here. This one, this one. These are hydrogen bonding. Oxygen attracted to hydrogen. White is hydrogen. This is delta minus. This is delta plus. See how they are attracted. And during this extensive hydrogen bonding, large gaps are left. And due to these large gaps, ice is less denser than liquid water. Now, what happens when you heat this? Now you start heating. What will happen when we heat? Can you explain as a chemist what will happen? No. What will happen when you heat? Explain like a chemist. As temperature goes up, kinetic energy goes up. Yes, the hydrogen bonds, the IMF, will start breaking. IMFs, they start breaking. And when you break these IMFs, what happens to these gaps? What will happen? Water molecules will come in between. The gaps will be covered. Now they are not bound by hydrogen bonding. So these gaps are filled by liquid water, right? As the gaps start getting filled by liquid water, what will happen to the density? Density, is mass per unit volume. So what happens to density? Density. Now, as these gaps are filled, so can I say there are more molecules per unit volume? Density increases. See here, the maximum density of water is at 4 degrees Celsius. 4. But if you further increasing the temperature, then what happens? You further raise the temperature, kinetic energy increases, and the molecules start moving away from each other. Yes, as the molecule starts moving away from each other, mass per unit volume decreases. So you can see how the density is decreasing. So maximum you can see here. So if I start with ice somewhere around -10, I start heating it. So initially the density will increase because ice has less density due to these large gaps. And this process of ice having less density than liquid water at low temperature is a life-saving process. Aquatic animals, aquatic plants, how they are surviving in extreme cold when the temperature is -20 or -10. Yes, Akash. When the temperature goes down, then God has all the tricks to save life. Nature wants us to survive. Remember this. If people are saying, oh, we are going to get killed, they all are negative people. So understand what nature wants. Nature wants us to survive. Nature wants us to be stable. Nature doesn't want to kill us. We get killed because of our mistakes. Okay, so here, if you see how nature is helping aquatic animals and plants in surviving extreme cold, because ice is less denser, so as the temperature drops, the topmost layer becomes solid. But below this topmost layer, beneath it, there is liquid. And this liquid, children, is warm because it is not exposed to external conditions, because the solid layer is acting like an insulator, like a blanket. It's a blanket to these animals and plants, insulator. We call it as a blanket provided by nature to all the animals and plants which are below this layer in liquid. So they survive extreme cold without any problem. You're understanding this? So this is important to know that ice is less denser than liquid water. Okay, now ion dipole forces I have already explained you. Remember Na plus in water, Na plus in, this is let's say H2O, OH2 is attracted like this. O is minus, H is plus, I minus in water. Now this time this is H2O, delta plus, delta minus like this. So this force of attraction is called as ion dipole attraction. I was explaining you hydration. Okay, can you explain this? What is this molecule, children? Now you have seen it so many times. What is this molecule? Yes, this is oxygen and this is hydrogen. What's the charge on oxygen? Use the right word. Yes, partial negative. That's the right word. Delta minus. Sometime when I ask what's the charge on oxygen, children they say minus. No, it's delta. Delta is like this. It's a Greek letter. Okay. So this is delta plus partial. Yes, like this. Yes, good. Okay, so now this question you already answered. This one has a stronger interaction because of high charge and small size. High charge and small size. Good. So both the factors are in favor of Mg2 plus. Okay, now we are doing some properties of the liquids, and after that we are going to do questions. Look at this liquid. Now in this liquid, if you look at the surface molecules, this surface molecule, this one, is it uniformly attracted from all directions? No. So what kind of force is there on this molecule? A downward pull, can I say? A downward pull. So all the surface molecules have a downward pull, which is called as surface tension. So the molecules on the surface, they are pulled inside. If I want to stretch them, no, not yet, Akash. You have done unit 2 test? Do unit 2 is already uploaded. And Amodita, you did it, right? I saw messages from your side. Okay. But you were doing quizzes from last 2 days. I saw plenty of them. Okay, good. Meng did it. Yeah. Okay. I'm going to upload one more test. I'll send you a message on WhatsApp. So the molecules on the surface are pulled in the downward direction, right? Downward direction. And if downward means they are pulled inside. If I want to stretch them, if I want to spread them, I need energy because they are pulled inside. They have an attractive forces which are pulling them down. So if I want to stretch it like this, we need energy to stretch it. That is called as surface tension. So, and the molecules which are inside in the bulk molecules, is there any force acting on it? What is the net attractive force on this molecule? Zero. It's uniformly surrounded from all directions. All the forces are cancelled out. So it's zero, right? So the net forces of attraction of the bulk molecule is zero because it's uniformly surrounded. On the surface, it's not uniformly surrounded. There is a net downward pull, which is called as surface tension. So if IMF is more, then what happens to surface tension? It's more. It's more, right? Good. But if surface area is more, what happens to surface tension? Surface tension is no. If surface area is more, if I spread it, more surface, don't you think that the molecules will have more unbalanced force in the downward direction? Surface tension is more. Mayank? Amodita? Yes, because if there are more molecules on the surface, then they are more pulled in the downward direction. So this is unbalanced force. Unbalanced. And this is balanced, all cancelling out. Which one nature is going to like? The unbalanced or balanced? The balanced. So what nature wants? High surface area or less surface area? Less surface area. So when water is falling, free fall, free falling water, is it going to fall like a flat spread out like this? Or is it going to fall like this? Which one is better? The second one. Because the second one has less surface area, it's like a sphere. Spheres, mathematically, in mathematics, we prove it also. We prove that surface area of sphere is less than that of the cylinder, square is less than that of the cube. These are the three-dimensional structures. So mathematically also, when I was in 10th standard, I used to do this type of questions. Okay. So strong intermolecular forces means high surface tension. Now the surface tension, which is a downward pull, then with this we have two more properties of the liquid. One is called as cohesion. Cohesion means they're attracted to each other. They have similar IMF, polar, then they are attracted to each other. Adhesion means not attracted. So adhesion means the molecules are among themselves only, not attracted to anything else. Cohesion means they're attracted to other part of the molecule. Like here, there is a glass. Any idea? Glass is made up of silica. So generally glasses are polar in nature. Polar. Yeah, polar. Silica, they are polar in nature. So glasses are polar in nature. And if you take water, this is water. Water is also polar. Glass is also polar. And glass has high polarity because of that oxygen and all these things. So what happened? That water is more attracted to the glass. And you will feel the level is going up. Can you see the level is curved like this? Up. Means as water is capillary action, water is rising like this. That is cohesion. So capillary action, how this is a plant, you put water in the roots, how the water is going against gravity. Water rises up against gravity because of cohesion. Because whatever tubes water is using, plants are using, like I think they use xylem and phloem kind of tissues, whatever they are using. So they are very polar in nature, and water can go up, can travel up with strong attractive forces due to cohesion. Is the word cohesion clear? But adhesion, here this is mercury. What kind of attractive forces are there in mercury? Yes, please. Mercury. What kind of attractive forces? Oh my God. Mercury. Come on. Yes, very strongest attractive forces as a liquid. Mercury is metal. Metal. It has free electrons around the mercury ions. Its attractive forces are metallic. Nothing doing with your IMFs. It's not a molecule. Metallic forces, yeah. Metallic forces are stronger than IMF. Mercury, you put a drop of mercury on the floor. What happens? Check it. There are videos on it. So when mercury is falling on the floor, it acquires the shape of a sphere. It doesn't spread because its IMFs are the strongest. It's not IMF. It has very strong attractive forces among the mercury metal ions due to electrons, very strongly attracted to each other. So they acquire the shape of a sphere to minimize the surface area. Mercury never spread on floor. Okay, and here this mercury has more stronger attractive forces, so it's not attracted to glass. So, oh, I'm sorry. I think I used the term differently. This is mercury. This is mercury. Cohesion means attracted to itself. Somehow I take this co means with the other. No. Cohesion means attracted to itself. This is mercury. In that case, it will appear like this. The capillary. Capillary will appear like this. This is mercury. Can you see it's not attracted to glass? So it's not clearly visible. Cohesion, I took the term with other matter, but cohesion is with itself. So mercury is attracted to itself. Can you see here also is going away, from the glass. It's not rising with the glass. But if this is water and this is glass, then it's rising, rising, rising like this. And in the capillary also, it will be marked like this. It's rising with the glass. So please do correction, adhesion and cohesion. Adhesion means with the glass, with the other material. Cohesion means with itself. So we are good with this properties of the liquids. Then we have another term, viscosity. Any idea what is viscosity? Viscosity is the resistance to flow. Like you have seen that oil and water, which can flow easily, water or oil? Water. So viscosity of the oil is more than that of water. So what is the reason that oil is less flowing than water? IMF. In oil, because of the big molar mass, oils have very big molar mass. Their molecules are big molecules. And due to higher IMF, molecules are holding each other. And because they are holding each other tightly, they have less tendency to flow. Okay. So viscosity depends on IMF. I'm going to give you this example, glycerol. See mercury, viscosity of mercury is higher than that of water, right? But how come this glycerol? Glycerol is maximum. Glycerol is even higher than mercury and water. So I'm giving you the structure of glycerol here. Glycerol, glycerine, these things are there in our houses also. CH2OH, CHOH, CH2OH. Can I compare this glycerol with water? So who has more stronger IMF, glycerol or water? What is the reason? The reason is more hydrogen bond. May I focus on this? More hydrogen bonds. there are more hydrogen bonds. That's why. The molar mass is big, but molar mass is not sufficient here. It's not very big. So you can say there are more hydrogen bonds. That's why this molecule is going to have higher viscosity, higher surface tension as compared to water. Okay, vapor pressure versus temperature. I'm giving you the structure of all of them. Diethyl ether, CH3, CH2O, CH2, CH3. They will be given to you in the examination. Water, Amodita, you are back, and mercury. Let's compare this temperature, 0. At 0 degrees Celsius, okay, here is the vapor pressure, right? So let's compare the vapor pressure is 1 atm here, 1 atm, this one. 1 atm is the normal pressure outside, 1 atm. This is the pressure around us. The atmospheric pressure is 1 atm around us. So which liquid has the lowest vapor pressure at this, which liquid has this pressure at the lowest temperature? Yes, the question is why. So can you compare their IMFs? Can you compare the IMF, this diethyl ether with water and mercury? Amodita, are you back? This is very important graph which I'm doing. So children, please, if you are saying 1 minute, try to come back in 1 minute. Okay, see here. Do we have hydrogen bonding? No, Akash, no hydrogen bonding. These hydrogens are on the carbon. Is there any hydrogen on this oxygen? No. The structure is like this. There are 3 hydrogens on this carbon. There are 2 hydrogens here. There is oxygen. There are 2 hydrogens here. And there is 3 hydrogens. If oxygen has a hydrogen, it would have been mentioned separately on it, and it would have been in the end of the molecule, not in the center. If it is in the center of the molecule and no hydrogen written on it, then it means it is bonded to 2 carbons. No hydrogen bonding, only dipole-dipole and LDFs. In this water, hydrogen bonding, dipole-dipole and LDF. So water has stronger. So water needs more higher temperature to reach this vapor pressure. Water has stronger IMF than diethyl ether. That's what I'm saying. Yes, yes, Akash, you are also saying the same thing. So water needs higher temperature to get this vapor pressure. Diethyl ether needs less temperature. What's the temperature needed? This one for diethyl ether. What's the temperature needed for mercury? 357. So I'm talking about the vapor pressure 1 atm. Diethyl ether gives us this vapor pressure at this temperature. Water gives at this temperature. Mercury gives at this temperature. The difference is IMF. The stronger IMF means more higher temperature needed. What is so special about these temperature? These are called as boiling points. Boiling point. So what is a boiling point? It is the temperature at which a liquid starts boiling. No. Now this definition is not sufficient. It is the temperature at which the vapor pressure of the liquid, the vapor pressure of the liquid becomes equal to the external pressure, equal to external or atmospheric pressure, external pressure. It means boiling points can be changed. Water boiling point is 100 degrees Celsius. For what pressure? For 1 atm, which is outside pressure around us. So this is your water. This one. What is the pressure here? 1 atm. Atmospheric pressure. Pressure means there are molecules which are exerting pressure in the downward direction. You start heating this water. Heat. As you are heating, what happens to the vapor pressure of water? It starts increasing, right? More vapors, more vapor. You'll reach a point when this pressure, this external pressure, and the internal pressure, this is internal. These water vapors are internal pressure. You reach a point when these two pressures are equal. When these two pressures are equal, then in that case means this internal pressure and the external pressures are equal, then in that case on the liquid there is no force. So what is the force acting on the liquid? Zero. And molecules are free to come out from anywhere, anywhere. Boiling is a bulk phenomena. Bulk means you can see bubbles coming out from the bottom. So boiling is the temperature at which there is no force acting on the liquid. Liquid is free to boil, free to come out of the liquid state into vapor form. That is boiling. Okay, this is the top of the mountain here. And this is the sea level. The pressure on the top of the mountain is, let's say, 0.78 atm. The pressure at the sea level is 1 atm. Now answer this question. Based on your understanding, what is a boiling point? Where the boiling point of water will be more? At 1 atm or at 0.78 atm? Yes, Mayank, you're right. At 1 atm. Because when external pressure is less, then I need less amount of heat to reach that external pressure. So liquids, water starts boiling faster on mountains. The boiling point of water is lesser on mountains, on the top of the mountains at high altitude, because pressure is less there. Mayank, you're understanding? Akash, you're there? And Amudita, you are still not back. Oh, you have to inform me, right? You missed a very important thing, this part. This part you missed, this graph and all these things. Very important. So watch the video then. Okay, so I have already explained you what is boiling point. So boiling point depends on IMF. Stronger IMF means higher boiling point. These things we have done. So these are two definitions of boiling point given. One definition I already explained you. This is that when the external pressure, the atmospheric pressure and the vapor pressure of the liquid are equal. External pressure generally 1 atm, that this is atmospheric pressure. But there is another definition which I want you to understand. We'll discuss more in when we are going to do heating curve and cooling curve. But right now, Let's see what is the other definition. The other definition is it is the temperature at which the liquid is in equilibrium with vapors. Definition, rest of the definition is the same, that the vapor pressure of the liquid is equal to the external pressure. But this is how we are going to represent the process. Liquid and gases are in equilibrium. This is boiling. The process is called as boiling. Then what can be melting? Melting. H2O solid in equilibrium with H2O liquid. This is melting. So boiling and melting, the phase changes are equilibrium processes. We are going to learn about equilibrium in unit 7. I think you are already aware of these phase changes. Just a review. So as you go from solid to liquid, what is this process called as? Yeah, so this is delta H of fusion. Remember fusion? And what is this process? Delta H of liquid to gas, delta H of. And what is gas to liquid? Deposition. Gas to liquid. Very good, Mayank. And liquid to solid? Freezing. And gas to solid? Gas to solid. Gas to solid is called as deposition. Sorry, this is condensation. Mayank, let's correct ourselves. Sometimes I see the answer in the chat and I generally say, oh, okay, it's right, but I'm always correcting it. No, not there is no term desublimation. It's just deposition, deposits. So gas is getting deposit on the surface as solid. Okay, and solid to gas is sublimation. So keep practicing these terms. But can I say, okay, now we know all these terms. Delta H, sublimation, delta H, fusion, delta H, vaporization. Can you tell me the relation between these three? Relation. Can I say delta H of sublimation is equal to, because energy can neither be created nor be destroyed. So can I say this? Can I say this? Understand these terms. Sublimation, if this is 20 kilojoules and this is 100 kilojoules, so what's the sublimation energy? This one. Sum of these two, 120. So understand these formulas. These formulas are not very clearly written in the books because they are expecting you to know about them. So write down this sublimation, fusion, vaporization, how they are related to each other. Okay, so okay. Now whatever time is left, we are going to do questions. So I'm already ready with the set of questions for you. Question 81. Type of solid means you have to tell me whether it is a molecular, non-polar molecular solid, polar molecular, like this. Okay. No, no, no. Type of solid. If I give you this as a solid, it can exist as a solid, Akash, at very low temperature. So what type? Is it a molecular solid, ionic solid, network solid? What is it? or metallic solid. We did 4 types of solids. Yes, it is non-polar molecular solid. It's a non-polar molecule. So what kind of IMF? London dispersion forces. So you're going to give me the type, the polarity, and the IMF, all 3 things together. What about this one, B? What about B? Network solid. No, it's polar. It's very polar, Mayank. There is oxygen. Silicon bonded with oxygen, then silicon, then there is oxygen here, then there is oxygen here. These bonds are polar. They are lone pairs also. It's not symmetrical. It's not symmetrical. These oxygens have lone pairs creating a very large dipole. It's very polar in nature. Glass, silica, sand. It's covalent network and very polar. So what kind of IMF this silica has? Dipole, dipole. Network, covalent IMF. Covalent bonding. So say covalent bonding. Don't say LDF or dipole, dipole. Say covalent bonding. You have to break these bonds to melt it. Okay, C. Yes, this one. We are on C. Silicon, carbon, they are. This is also covalent network. Not as strong as diamond and graphite, but it's very close to carbon. So this is also covalent network. And here is covalent bonds are there. Okay, what about D? D. What type of solid? Ionic, molecular, covalent network, metal. Yes, it's molecular. What about this? Ru, ruthenium. E, ruthenium. Please type the number also. E, ruthenium. Check in the periodic table where is ruthenium. Check for D block. It's a metal. It's a metal, right? So what type of solid is this? Metallic solid. What kind of attractive forces? Metallic forces. Don't call it as non-polar. It has? Oh, okay. You're understanding this E? Did you search E in the periodic table? Yes, metallic attraction. Amudita is right. Let's go for F. I2. Yes, molecular solid. Non-polar, LDF. Let's go for G. Mhm. Yes, ionic solid. Mayank, you can say ion-ion attraction here. Don't say polar or dipole. Ion-ion. Children, ionic solids, ion-ion attraction. Call it as ion-ion, okay? Mayank and Akash. Ionic solid, ionic attraction, the way Amodita has said. H. So H. Mhm. Simplest molecule, molecular solid, hydrogen bonding, dipole, dipole, LDF, molecular solid, right? NaOH. Now you're going to give me only major attractive forces, major. Oh, Mayank, it's ionic. Give me the major ion-ion attraction, isn't it? Ionic bonding, okay. The major is ion, Na plus with OH minus. This is the major attraction. Hydrogen bonding cannot exist here because these two are major. They are not making hydrogen bond with each other. So it's ionic attraction. Uranium, J. Uranium. Oh, uranium is what? Mayank? You're answering J? Again, only Amodita is right. Amodita is saying metallic, is metal. Uranium is metal. Mayank, uranium is metal. It's not a molecule. We have different types of, you remember I said 5. One is polar molecules, 5 types of solids. You can see my notes. Second is non-polar molecules. You are going to call them as molecular solids. Third is network, covalent network, which is the strongest. Fourth is ionic, metal with non-metal, ionic. Fifth was metals. So every time you're forgetting about metal. Yes, Mayank, K is right. Ionic solid, but don't say polar, say ion-ion attraction. Okay, the attraction here is, major attraction here is ion-ion. Polar is slight separation of charges. Do we have slight separation of charges? No. So first you write ion-ion attraction, after that whatever you want to write. The major attraction is ion-ion attraction. Last, pH 3. That's the perfect answer. pH 3 is a molecule with 3 hydrogens like this, and it has a lone pair. It is not a symmetrical molecule, so that's why it is polar in nature. Yes, very good. That's one type of question. We have 2-3 minutes. Can we do similar one more, 82? This one? No, this you can try on your own. Let's do one question from here. All these are not the part of our study, these things. We are not learning them. This is college level. Okay. Can we do this 42? Very fast, okay? I'm not going to take much time. Highest boiling point, which one? So first you identify. Are they polar, non-polar? Are they polar, non-polar? What type of IMF? Depends on molar mass and size. Which one has the highest molar mass? CBR4. That's with the highest molar mass, bigger surface area. This one has the highest boiling point, right? Check this. Lowest freezing point. Lowest freezing point means it's going to melt easily. So, which one? Yeah, very good, very fast. Amodita, that's really fast answer. Smallest vapor pressure. Smallest means very strong IMF, right? It's difficult to vaporize it. That's very good answer, Amodita. Akash, very good. Yes, D. Greatest viscosity, again strongest attraction. High viscosity means molecules find it difficult to move because they are strongly attracted to each other. That's really very fast and very good answer. E, greatest heat of vaporization means more heat is needed. More heat is needed to vaporize it. Greatest delta H of vaporization is very high. High delta H of vaporization means IMF high, strong. Yeah. So this is polar, right? These are non-polar. This one is polar. If you draw the Lewis dot structure of this molecule, it's like this. It has a very big polarity here, delta plus, delta minus. Mayank, you can see this? Yeah, good. Smallest enthalpy of fusion, very small energy needed to fuse it. Fuse means to melt it. Small. Small means less. So IMF is, you're looking for less IMF. Yes, I2. Perfect answer. So that's the end of your 3.1. 3.2, 3.3, I have seen Mayank and Amodita are already doing the quizzes. I think you also did some quizzes, Akash, on 3.2. So do these quizzes, 3.2 and 3.3. And if you feel that you could not do very well in that, do it again because today we finished with all types of solids. Okay, and then I'm going to start. Next class is for gases, one of the most important topic for any examination, gases. Yes, so we are covered with, we have already done 3.1, 3.2, 3.3. I'm moving on 3.4, which is gases. You have to practice and plenty of questions over there. We need a calculator. So bring your graphing calculator. Children, I have already posted the video given by Akash. Thank you very much, Akash. Your video is getting popular on the website also. I'm generally giving it to all my students that watch this video and see how to use it. So you should be ready with your graphing calculator also so that we can do questions. So see you in the next class. If you have any questions, you can stay back. Bye. Bye-bye.